Well, first, I just want to say thank you so much for inviting me to the CCA Zoom room today. It's really such a treat to get to share science, especially these days while a lot of us are stuck at home for the time being. The title of my talk is Let the Great World Spin, revealing the turbulent, stormy atmospheres of giant planet analogues. And when I say giant planet analogues, I'm primarily talking about brown dwarfs. Now, brown dwarfs are the lowest mass products of star formation, and they're really the missing link between low mass stars and giant planets. Although they likely form like stars, they don't have the necessary mass to sustain hydrogen fusion, so spend their lives cooling. The hottest brown dwarfs we know of have temperatures of about 2,600 Kelvin, and the coolest brown dwarf we know of has a temperature of about 250 Kelvin. So some of them can be really, really cold. And the coldest brown dwarfs really overlap with the temperatures of planets. So we can often think of them as exoplanet analogues. They have similar temperatures, similar sizes, and in many cases, they have similar ages and masses. But they're much easier to observe without the glare of a bright host star. And in studying these objects, brown dwarfs, it can provide a lot of insight into what we might expect for giant exoplanets in the future. So this plot is showing evolutionary temperature curves of low mass stars, brown dwarfs, and giant planets. And all of these lines here represent objects with different starting masses. And as I said in the last slide, the defining characteristic of a brown dwarf is that it cannot sustain hydrogen burning in its core, so can't produce its own energy. So while a low mass star will reach the main sequence and continue to burn for billions of years, a brown dwarf simply can't produce its own energy. So it will continue to cool throughout its life. If you take a lower mass planetary mass object like this purple circle I'm showing here, which has a mass of about 5 Jupiter masses, it will cool down a lot faster. It'll start out cooler and reach a temperature quite quickly. And this actually results in this inherent age mass degeneracy for brown dwarfs. If you measure the temperature of a brown dwarf you see in the field, you actually can't tell the difference between a really high gravity brown dwarf that's old or a really low mass brown dwarf that's young. So we always need additional information about an object's youth if you want to then figure out its mass. And I'll get back to that a little bit later. But a few really interesting things happen when you allow an atmosphere to cool. The first of which is that molecules start to form in the atmosphere. So here's a bunch of spectra arranged in terms of temperature, with the hottest on top and the coolest on the bottom. And for an M8 brown dwarf, you can see that the spectrum looks nearly like a black body, but you can see absorption bands due to H2O there. But as you cool down further into colder brown dwarfs with colder spectral types, you see that molecular absorption becomes more and more important. So for instance, these water absorption lines get deeper and deeper, and then you start to see absorption lines of new molecules such as CH4 or methane, which I'm showing here. So the coldest brown dwarfs really depart from black body curves in that way. The second thing that happens in a cold atmosphere is that you start to get clouds forming. So in this plot, I'm showing you the pressure temperature profiles of some brown dwarfs of various temperatures, as well as Jupiter on the left and the sun on the very right. And if you're looking down into an atmosphere, you're looking down into higher pressures and to the right to higher temperatures. So that's kind of why they all have that similar shape. Now in green, I'm showing you the condensation curves of various species. And wherever a pressure temperature profile intersects with one of these curves, the molecules condense from the gas phase to form droplets or grains, which can then build up to form clouds. So I can also put in the approximate positions of the clouds from this diagram. And some of the types of clouds we see are very alien to us on Earth. So for an L dwarf, for instance, shown in the purple, we get clouds composed of magnesium silicates, iron droplets, and aluminium oxide. When you go a little bit cooler again to the T dwarfs, you get potassium salt and sulfide clouds. And those clouds actually form deeper in the atmosphere, so at higher pressures. Cooler again, you get to the Y dwarfs, which are actually cool enough for water clouds to form. And then finally, for Jupiter temperatures, you'll get ammonia clouds. And the ammonia clouds are those white fluffy clouds we've all seen on Jupiter. And this is kind of just a cartoon summary of all that, but it's showing as you cool from M to L to T, you're just essentially collecting more and more types of clouds. Each cloud species will form when the pressure temperature profile intersects with a condensation curve. But as the atmosphere cools further, that intersection essentially just sinks deeper into the atmosphere. So by the time you get to temperatures like we see on Jupiter, all of these clouds of corundum and iron and potassium sulfide, they're still there. They're just really, really deep in the atmosphere where you can't see them. With the ammonia on top. And these clouds have a really huge effect on the colors and spectra of brown dwarfs, and particularly across the L and T spectral types. And this is best shown on a color magnitude diagram, which I'm showing here. So for those not really used to looking at these, up means bright, right means red, and left means blue. And as a brown dwarf cools throughout its lifetime, it follows this sequence, M to L to T, and eventually to Y. And below temperatures of about 2,200 Kelvin, we get condensates such as iron and silicates building up to form high altitude clouds. But as the L dwarf continues to cool, these clouds keep building up and become thicker. And this causes the late type Ls to become increasingly redder in the color magnitude diagram. In contrast, the atmospheres of T dwarfs appear relatively cloud-free. And the clouds here are thought to have sunk below the photosphere where we can't actually see them. So then on the color magnitude diagram, the T dwarfs appear at least a magnitude bluer than the hotter L dwarfs. And the transition between the L and T spectral types, which we call the LT transition, is not very well understood. The transition happens over a very narrow temperature range of only about 200 Kelvin. But it's accompanied by this really dramatic blueward shift in the color magnitude diagram and a disappearance of these thick condensate clouds. And during this transition, the clouds are thought to break up, become patchy, and gravitationally settle below the photosphere. So my kind of cartoon version of an LT transition appears to have these patches of clouds in its atmosphere. And my research really focuses on trying to detect and characterize these patchy clouds so that we can learn more about the atmospheres of both brown dwarfs and giant exoplanets. And the reason we can actually detect clouds on a completely unresolvable point source is that they have relatively fast rotation rates. And we can directly probe the presence of these atmospheric features as they rotate in and out of view by looking for photometric or spectroscopic variability in their light curves. And variability has been carried out for about a decade at this stage, and multiple surveys have shown that cloud-driven variability is actually very, very common. And in the last decade or so, we've learned so much about brown dwarf atmospheres through variability studies. Because once you detect variability in a brown dwarf, it really opens up a whole new window into the atmosphere. And for that reason, we really jump for joy when we detect cloud-driven variability in a brown dwarf, because that means that we can really characterize that particular object in unprecedented depth. So here's a few things that we can do in a variable brown dwarf. Of course, I cannot talk about all of these in detail today, but briefly, using spectroscopic monitoring, we can learn about the cloud particle size and distribution. And we can also gain insight into the effect of surface gravity and youth on the atmosphere. We can even sometimes detect multiple cloud decks in the atmosphere. And we can measure viewing angles. We can sometimes construct spatial maps of the cloud features. We can also measure their rotation rates and their winds. But today I'm going to touch on the surface gravity, the viewing angle, and brown dwarf winds. So first up, I'm going to talk about how we can use variability monitoring to understand the lowest gravity atmospheres. And as I mentioned earlier, if you want to look for the lowest mass objects, the key is to look for things that are young. So I often kind of use low gravity, low mass, and youth interchangeably. And we have two tools to identify objects that are young. Brown dwarfs. So yeah, the first off, which I'm showing on the left, is that you can look for signatures of low gravity in their spectra. So for example, here in the H band, which is in the middle panel, you can see that the shape is very different for low gravity and field objects. It's like very triangular shape for the low gravity objects, but it has a more rounded top for the high gravity objects. So we can look for signatures like this to try and find the lowest gravity objects. On the right, I'm alluding to identifying members of young moving groups. And these young moving groups are made up of both stars and brown dwarfs that formed as part of the same molecular cloud and then dispersed. But they still share some kinematic properties, so we can still identify them. And these are super useful because it allows us to construct an age-calibrated sample of brown dwarfs with known ages and estimated masses. And in recent years, a significant number of young brown dwarfs with low masses and surface gravities have been identified. So here I'm showing you yet another color magnitude diagram. When you plot the young low surface gravity objects on the diagram, you can see that they form their own distinct sequence. So for a given spectral type, they're consistently redder and less luminous than the field brown dwarfs. So this low gravity L sequence is shifted to the right and extends down to fainter magnitudes. And to explain these kind of different colors and spectra of low gravity objects, models generally invoke disequilibrium chemistry and thicker clouds that extend to lower pressures or higher altitudes. So since it seems that the low gravity seems to affect the properties of the clouds, it is likely to expect that the cloud-driven variability will exhibit some sort of gravity dependence also. And finally, I've just plotted a few of the directly imaged planets that we've detected so far, and you can see that they fall on this same sequence. The low gravity dwarfs act as really powerful analogs to the directly imaged planets and are much easier to observe. So by studying the variability of these free-floating planetary mass objects, it might provide clues as to what we will expect from the directly imaged planets. And we've seen some hints that the variability properties may be different. So there is a small but growing number of low gravity brown dwarfs with very large variability amplitudes. And two recent ones, which I'm showing here. On the top, I'm showing PSO 318, which we detected variability on this object back in 2015, and it was actually the first planetary mass object with detected cloud-driven variability. And this showed this huge variability amplitude of about 11%, which we had never seen before for an L dwarf. Then on the bottom, I'm showing you discovery from this year, in which they detected an amplitude of 25% variability in the J band, which is absolutely huge for this late L intermediate mass companion. And in, here we go. In 2019, I carried out a variability survey. And so this has been the only actual survey that has been carried out so far in the low gravity objects. And we found that the low gravity exoplanet analogs are much more likely to be variable than their field brown dwarf counterparts. So these young planetary mass objects were about 30% likely to be variable, whereas the higher mass field brown dwarfs are about 10% as likely to be variable. And since this initial variability survey, we've moved on to using the Spitzer Space Telescope, which has several advantages over ground-based monitoring, but I would say the most important is that we can observe for these really long durations that you just can't observe from the ground or even with HST. So for instance, we can observe an object for 40 hours without any interruption. So on the right, I'm showing you two brand new variables that are both low gravity. They both have masses of about 20 Jupiter masses, and that we published this year. And the pink points and the green points are showing you the Spitzer channels 2 and channels 1. And both objects were variable in both channels. And in this paper, we combined these two new variables with the full sample of brown dwarfs, whether they're high or low gravity, that have been observed with Spitzer. And here I'm showing you young and field objects that have been monitored with Spitzer at 4.5 micron. So it's a spectral type color diagram, so similar to the magnitude diagram I was showing you earlier. The symbol size here is showing you the amplitude of variability. Field objects are in blue, young objects are in pink, and the darker colors represent actual detections and the lighter colors represent just upper limits. And as you can see, we do have a decent sample size to actually explore the variability properties. So first we looked at the variability amplitude of the low gravity and field samples. And right away, we see that there's this enhancement in amplitude for the late L objects. And the late L objects have amplitudes much higher than the field L7s and much higher than any early L dwarfs, whether they're young or old. We do not see the same enhancement at 3.6 micron, but I wouldn't give up on that yet because we just haven't observed the same number of objects at 3.6 micron. So I wouldn't make any big claims yet. And also, as luck would have it, we actually have a lot of 3.6 micron data coming soon. This is one of the last large surveys carried out by Spitzer before it was decommissioned. So we will have an answer to this very soon. But it does seem like the young objects seem to show enhanced variability in the near and mid-infrared. And the reason why might lie in the models. So Diana Powell is a grad student, a final year graduate student at UC Santa Cruz, and she's working on models investigating the formation of clouds in low gravity atmospheres. And on the left, I'm showing the formation of clouds in a high gravity atmosphere, and on the right, the formation of clouds in a low gravity atmosphere. And the main difference between these two models is that the clouds form at higher altitudes in low gravity atmospheres. So this means that if these clouds then start to become patchy, we're observing a greater temperature difference or a greater contrast between the cloudy and less cloudy patches. So this may be one explanation for why we're seeing enhanced variability. And for this paper, we also decided to investigate the viewing angle of as many brown dwarfs as we could. So if you have a measurement of the rotation period of a brown dwarf, which is a pretty easy measurement to make from Spitzer variability monitoring in particular, we can combine this with a V sin I measurement, which you can get from a beautiful high resolution spectrum like the one I'm showing here. And you combine those with a radius estimate and it will give you the inclination or the viewing angle of each brown dwarf. So the first thing we looked at related to inclination was the amplitude. And we expect that the inclination would have some effect on the variability amplitude. So these two plots are showing you inclination on the y-axis, where 90 degrees corresponds to equator on, and 0 degrees corresponds to pole on. On the x-axis, we have 3.6 and 4.5 amplitude. And we see this dependence of variability amplitude on the inclination angle. So the bottom right-hand corner is completely empty in both plots, which means there's no high amplitude objects inclined close to pole on. All of the really high amplitude variables are up closer to 90 degrees. And then we don't even have any variability detections at inclinations less than 20 degrees. And this makes sense geometrically, because if we assume that clouds are located at the equator, rotating around the equator, if we observe equator on, we'll measure the full variability amplitude, whereas if we're just looking down on the pole, we're not going to observe any variability because the clouds aren't rotating in and out of view. And variability studies have kind of always assumed that there was going to be some inclination dependence, but it's really nice that we're starting to be able to actually show this empirically. The second thing we discovered was not exactly expected. So the second trend I'm showing you here is this possible relation between inclination, so again 0 to 90 degrees on the y-axis, and J minus K color anomaly on the x-axis. And the J minus K color anomaly is the difference between an object's color and the median color for that spectral type and gravity class. So basically anything with a positive color anomaly looks redder than the median, and anything with a negative color anomaly looks bluer than the median. And based on this plot, it seems that objects viewed equator on appear redder than the median, and objects viewed pole on appear bluer than the median. And this was definitely initially puzzling, but we did come up with one idea in which this could be explained if you think about how clouds are distributed latitudinally. So if clouds are thicker around the equator, relative to the poles, this might be pushing the colors towards the red end of the spectrum, primarily for the equator on objects.
Johanna, is that that latitudinal distribution, is that something that we see in the solar system planets, thicker at the equator and thinner at the poles?
Yeah, I'm going to talk about Jupiter in 2 slides time. And in fact, this has been found using 3D atmospheric models of brown dwarf and exoplanet atmospheres by Jianyu Tan and his collaborators. So here I'm showing you the cloud profile from their simulations, which shows you the local cloud thickness at each latitude from -90 to +90, for 4 different rotation rates from 20 hours to 2.5. And this simulation shows that the local cloud thickness is generally thicker at low latitudes and smaller at high latitudes. And this is particularly the case for the fastest rotators. And this is generally due to the Coriolis force. And as Kelly alluded to, if we look at Jupiter, which I like to call our closest brown dwarf, the Juno mission recently revealed Jupiter's poles for the first time, showing that they are very different to the equatorial bands we observe at the equator. I'm not 100% sure about the thickness at the poles in the equator and whether they've actually made that measurement, but they're certainly very different. And the lovely blue poles of Jupiter were not totally expected. So we won't be able to resolve a brown dwarf anytime soon, but we might be seeing the first glimpses of this phenomenon in brown dwarf atmospheres. And for the last part of my talk, I'm going to talk about some very recent efforts we just finished to try and determine brown dwarf wind speeds. Okay, so looking at the gas giants for inspiration, for both Jupiter and Saturn, measuring wind speed isn't particularly taxing because we can pretty easily resolve Jupiter's atmosphere. We can trace atmospheric features rotating in and out of view and measure the zonal wind speed. So here I'm showing you the zonal wind profile of both Jupiter and Saturn. So how fast is the wind speed at different latitudes? And if we focus on the equatorial area, you'll see that the equatorial band is rotating with a positive velocity with a mean speed of about 100 meters per second for Jupiter and 400 meters per second for Saturn. Now this is not something we can do for brown dwarfs anytime soon, because as I mentioned earlier, we're not resolving them. But there's actually a second way to make this measurement. And that's by focusing on the rotation periods of Jupiter. So there's two ways of measuring the rotation period of Jupiter. The first method is what I've been talking about for the last 30 minutes or so, and that's to trace atmospheric features as they rotate in and out of view. So if you do that for Jupiter, focusing on kind of equatorial features from +10 to -10 degrees, you'll measure a rotation period of about 9 hours, 50 minutes, and 30 seconds. But Jupiter also emits aurora. I'm showing you the UV aurora here, but these aurora are also emitted through beams in the radio, which can be modulated by its rotation. And since Jupiter's dynamo lies, I think, at least 7,000 kilometers below its surface, when you're probing this radio period, which is powered by the magnetic dynamo, you're actually probing the kind of nearly rigid body rotation of the interior of the planet. So if you measure the period using these radio pulses, you'll measure a period of about 9 hours and 55 minutes and 30 seconds. So Jupiter's interior is actually rotating 5 minutes slower than its atmosphere. Excuse me. And then you can change that 5-minute difference into a velocity difference, and you'll end up with a wind speed of about 100 meters per second, which matches what we found earlier. So I think you'll probably believe me that brown dwarfs exhibit cloud-driven variability, but what about aurora? About 10% of brown dwarfs emit radio aurora, similar to what we see on Jupiter, but kind of souped up with much stronger magnetic fields. The signal we observe is pulsed, circularly polarized emission, which is consistent with aurora, like we see on the planets. And this is a kind of a newish field. It's super interesting, so I've just put a bunch of papers here if anyone wants to delve in. And this is just a really nice visualization of the radio aurora emission, in case anyone's wondering. So the polarized radio signal is emitted from these two emission cones that lie near to the magnetic axis, which will be slightly offset from the rotation axis. And basically when the beam is pointed towards the Earth, we'll measure this strong, short-lived radio pulse. And since radio aurora is a lot less common than cloud-driven variability, we chose a sample of pulsed radio emitters and went after them with Spitzer to look for cloud-driven variability. And we got a hit for one object, for 2MASS 1047, which is a late T dwarf with a temperature of about 900 Kelvin. And this is the coolest known object outside of our solar system that has radio bursts consistent with aurora. So we use Spitzer to measure the upper atmosphere rotation period. We observe this object over two different epochs, one of which I'm showing you here. And in both epochs, we detect very sinusoidal variability with the same amplitude in our target. And then we use two methods to measure the rotation period, one being a periodogram and bootstrap method, and also an MCMC sinusoidal fit to the data, which I'm showing you here. Both methods agree, and we get an infrared period of 1.742 hours. Next, we went back to observe this object in the radio again to kind of pin down the radio period even more. So we observed at 4 to 8 gigahertz with the VLA for 3 nights in a row, as you can see in the 3 panels here. We observed this periodic circularly polarized radio bursts that are expected of radio emission. And again, we actually used two methods to determine the period. The first of which is the time of arrival analysis that was developed by Peter Williams, one of our co-authors who is the radio expert. And we also used the same periodogram bootstrap method we used before. And both methods agree, and we get this kind of period range for the radio. Okay, so we measured two different rotation periods, but the question is, are they different enough to claim a wind speed? So we put it through the equation, and yes, we measure a positive wind speed of just under 650 meters per second, and with a pretty hefty uncertainty of 300 meters per second. But overall, we detect this positive wind speed at over 98% confidence. And this is the first atmospheric wind speed measurement for any cool substellar object outside of our solar system. And just like Jupiter and Saturn, the atmospheric period is shorter than the interior period, indicating a super rotating atmosphere. The wind speed is higher than both Jupiter and Saturn, which agrees with theory, which would predict that larger atmospheric heat flux would drive stronger winds. And then just finally, I'd like to kind of briefly reflect on what all of this work means for the future moving forward. And when I think of the future, I really think about JWST observing directly imaged planets, such as the HR 8799 system, which I'm showing here, which is an amazing system of 4 directly imaged planets. And we've been observing these planets for over a decade. So if you put all of the images together, we can actually watch them rotate around their host star, which is really, really amazing. And all 4 planets have late L spectral types. So everything that we've done for the low gravity object brown dwarfs at L spectral types is really informing what we think we're going to do for these. So we've done so much work on brown dwarf variability over many years, and this means that we're really ready to move on to detecting variability in the directly imaged exoplanets. We've all the tools ready to go and have learned some very valuable lessons from the free-floating planetary mass objects. And the first lesson is that the directly imaged exoplanets are very likely to show cloud-driven variability. In the near infrared, we have evidence of a higher variability occurrence rate, and we specifically see very high amplitude at spectral types of around L7. So that's exactly where these HR 8759 planets lie. Lesson 2, however, is that the viewing angle really matters. So while I think it's very likely that these planets host the sort of atmospheres that would show you variability, they're also probably inclined pole on based on their orbit. So we may be unable to detect any variability. And for this reason, we may actually be better off targeting an exoplanet that is likely inclined equator on, like Beta Pic b, which I'm showing here. Lesson 3 is possibly more my personal feelings than an objective fact, but I really think it will be worth it. If we can detect variability in a directly imaged exoplanet, it will open up a whole new range of characterization possibilities for that exoplanet. We can fully characterize the atmosphere and the clouds, and even measure the winds on these distant worlds. So in summary, if you leave this Zoom room with one piece of information, I hope it is that brown dwarf variability monitoring is extremely useful. I showed you that low gravity L dwarfs show enhanced variability in the near infrared and the mid infrared. And this is likely a result of higher altitude clouds that form in low gravity atmospheres. I also showed you that the viewing angle affects the observed variability amplitudes and may also affect the observed colors of brown dwarfs. And then finally, I showed you a brand new technique that we just used, which combines infrared and radio monitoring to measure the wind speed in brown dwarf atmospheres. And I look forward to the future. So thank you so much for taking the time to listen, and I would be super happy to take your questions.
Thank you so much, Johanna. That was awesome. Yeah, so it looks like Mordecai already has a question, and so let's go ahead and use the raise hand feature so we can start a queue for questions. So go ahead, Mordecai.
So I was just trying to understand how brown dwarfs have aurorae, because my understanding of planetary aurorae is there's a solar wind that flies along and runs into the planetary's magnetosphere and then runs down and hits the atmosphere. But the brown dwarfs must be generating their own aurorae. Do we have any idea how that works?
Yes, we have an idea, but no, we don't exactly know what the answer is. But one option is that if you look at Jupiter, Jupiter's aurorae are also actually powered by its interactions with Io.
Oh.
So Io generates this kind of flux tube between Jupiter and Io, and that generates aurora in the atmosphere. And that remains a possibility for brown dwarfs. Maybe the 10% that show aurorae have satellites. There are also other alternatives.
So you're saying you're discovering brown dwarf planets just incidentally here?
I'm not going to claim that, but it remains a possibility. They're definitely the 10% of objects that emit.
Have you looked for transits in your variable objects?
Yes, we have. We have not found a transit yet for a brown dwarf, but we lie in hope.
So Jupiter has a persistent aurora as well as the hotspots from Io and Europa and things like that. And these auroral stars also have a persistent radio emission. It's probably from something known as co-rotation breakdown, which is this shearing current
right, where the
generated.
field is spinning around too fast to keep up.
Yeah.
Kind of like a pulsar.
I don't see another hand, even though I very much look forward to more hands coming out.
I have a hand. So,
Go ahead, Denton.
question, Johanna. That's really interesting work. I've caught up to speed on this. Are the condensation calculations you're using, those are pretty much the Lotus and Fedley 2004 curves? Has there been any new work since then?
I would have to look up what the state of the art curves are. I'm sure they've been, I'm not sure actually.
All right, I'll think about
I can look it up and let you know.
Tom?
Hey, Johanna, great talk. I have a question that you might have been able to predict just based on my own interests, but besides this cloud thing that you point out, are there other variability mechanisms that you see commonly in brown dwarfs?
For brown dwarfs with spectral types later than like L5, we generally think most variability is cloud driven. There does remain a possibility, and a lot of people have been working on whether brown dwarfs emitting aurora, is there also a near infrared part of the aurora that we've been missing? And so far studies that have just, compared the object that emit aurora with the objects that have infrared variability, those objects don't actually, in general, they're not the same. So very few objects are actually like this object that I just showed, 1047, that has both. And then for the early Ls, it's a little bit hazy because, kind of the ML transition, we could be seeing magnetic spots. And I'm not sure I'm not sure what the latest spectral type with confirmed magnetic spots are, but we definitely don't know where the cutoff is. So that's something we would worry about for the earliest L spectral types.
Thank you.
And Tim?
Yeah, I was thinking of a spot question as well, how you might distinguish between clouds and spots. And then I had another very naive question, so I'll do the somewhat smarter question first.
That would be done using spectroscopic variability monitoring, which I haven't showed, which I didn't talk about today. But basically we can, based on the shape of the spectrum as it changes, you can test those kind of models.
Okay.
And we haven't seen spectroscopic variability consistent with magnetic spots yet. So
the silly question I have has always been this definition of winds. And on the giant planets, it's definitely a zonal wind. And this internal wind is sort of a newer sort of wind concept, in my mind at least. But like, if we're looking at zonal wind and there's an object like the sun that's rotating differentially, nobody ever talks about winds on the sun. And I mean, and now we have brown dwarfs, which have winds. And so, are we looking at, is there a difference, or is it semantic between differential rotation, actual zonal winds? Now you've got this internal external wind. I'm a little getting stuck on the verbiage, I think.
Yeah, I think, and we have, like for brown dwarfs, we've kind of seen hints of differential rotation too, so it does get a bit confusing. And I think the difference between what we've observed here is that we're really measuring like the bulk wind speed of the atmosphere as like compared to the interior. But, if we could delve in, if we could just see a brown dwarf up close, we could do that zonal wind profile that I showed you for Jupiter and find that it is actually all moving in different relative directions and at completely different speeds. But I wonder if, differential rotation on the sun is more classified as flows, and we think of winds because it's just gases all the way down.
Mhm.
Maybe.
Our Earth-centric nomenclature coming in.
Yeah.
Jackie?
You actually do. I have many questions about all of this. But I think what might be nice to talk about is, since some people on here might end up being on a JWST tack, maybe, can you comment on what we're going to see in the, say, spectra of JWST? And so like the spectroscopic kinds of ways we can go after these objects with JWST versus the photometric ways we might go after them.
Yeah, I think, yeah, JWST gives us a really great opportunity to get really high resolution spectroscopic observations, like much higher than we've already had. So we actually have some evidence that, you know, with so we do expect to see differences in the variability properties within some absorption lines, for instance, the iron absorption line. But I have seen some results so far that say with the HST resolution, we actually wouldn't be able to detect something like that at all. So just getting the near infrared, which is the same wavelength we've already been targeting, but at higher resolution, will be amazing. And then secondly, getting spectroscopic variability in the mid-infrared will be like absolutely mind-blowing, because we literally lost the mid-infrared with Spitzer the same year that we discovered variability was a thing, which is super, it's super unfortunate, because the very thing we think that is causing variability, which is these silicate grains, has this massive feature at 10 microns, which we've never been able to observe in a brown dwarf. So I think spectroscopic observations of, you know, that 10 micron area of a variable object will just tell us a lot about what is going on in the atmosphere.
There's some chat about the Roman telescope. Tim, do you want to?
No, I was just trying to change habits from calling it JWST to, no, sorry, I was no, I had nothing to add. No.
Right. Roman is the W first, right? It used to be called W first.
Yeah.
That might be a good segue, though, to if you want to say anything about the Rubin Observatory and what it'll do for variability studies. Not a question you asked him, but one Johanna could answer.
I actually don't really know. I haven't looked into it very much, but it would depend how faint it can go, which I'm not sure it'll go super faint enough. But it might give us the opportunity to probe long-term variability, which is a massive unknown for brown dwarfs right now.
Ruth?
Hello. My question is somewhat related to Tim's, but do you have a sense of, like, do you see quasi-variability in the brown dwarfs? Do you think that you see some cloud patterns changing or anything, or like do you see like distinct cloud lifetimes?
Yeah, so that is a very that's a great question. We do see a lot of like variables, we call them. So they're always variable when you look at them, but the light curve changes like completely. You know, between one rotation and the other, it can really change a lot. It's normally explained by the clouds evolving themselves, but recently it's also been put forward by Daniel Lapai and his team that the variability is being caused by like zonal cloud bands that are moving differentially to each other. So they're nearly like beating to cause this variable light curve. But because we honestly have so few objects that we've observed, you know, more than 10 or 20 rotation periods. It's really, really hard to say exactly. But yeah, that's something I'm really interested in.
Right. So maybe like eventually, if you had enough data, you could see how variability varies on that CMD or something, and try and make some inference about what's causing it. Thank you.
I have a question about the super awesome wind result, which is that, you know, the data set that you have for that result is really impressive. And I'm surprised, like I wouldn't have predicted that you would have that type of measurement from such a cool in temperature, low temperature object first. And so can you comment at all about why you think the wind measurement, you were able, that it was made first with a late T as opposed to a late or an early L?
Yeah, that's a good question. I think so to measure the wind speed, you know, we needed a radio emitter. So we had like a list of radio emitters, pulsed radio emitters. And in order to measure the best rotation period, honestly, the fastest rotation period is best. And the T dwarfs are rotating rotating faster than your average L dwarf. So from the radio side, it's easier to measure a rotation period of a T dwarf just because you get more rotation periods per night. And then, yeah, I mean, we did observe originally 2 or 3 candidates, and only one of them appeared to be variable. So that's where the drawback is, because it was fairly faint.
Right.
So it's
Fairly
hard to
faint.
detect
I think
variability.
it's an understatement.
Yeah.
And Stacia was asking how fast they rotate, and I think we're talking about hours or under an hour. What is, yeah.
Yeah, so this object was 1.7 hours, which is very quick.
Cool. Stacia, go ahead.
I just wanted to kind of a comment. I hate people who comment, but just for the talking about the clouds and how they maybe thin out at the poles. I don't know for Jupiter really, but for Neptune, they really do thin out at the poles extremely dramatically. Neptune rotates much more slowly, so it's probably got different zonal wind patterns, but it does seem to, you know, it is something that I could imagine happening for sure. So that is really, really interesting to me. It's like big holes at the poles, like down to maybe 60 degrees or so. So it's pretty dramatic.
What's the rotation period of Neptune?
Neptune is 16 hours, I think.
Okay.
So it's much slower than a couple hours. And I think that Jupiter is supposed to have, you know, because it's faster, that kind of breaks it up into those bands. So I would kind of expect a really fast rotator to break up into even more bands.
I wonder we have data from Venus, which is the slowest rotator of them all.
But it also has the thickest clouds, like the most, like I feel like it's almost easier to measure the thickness change if it goes from thick to what Stacia was saying, like thick to holes. But if you go from super thick to just less thick, it might be a harder measurement to make. I'm just guessing.
And very windy in the high atmosphere, right? Because people originally thought it spun, you know, like with a day period roughly, like the Earth, and it turned out to be completely wrong. So just based on the atmosphere is going around a lot faster, the upper atmosphere. So it's bizarre.
I'd be nervous about using Venus to try to think about this though, because Venus has a surface, and surfaces interact with atmospheres a lot.
But there's no wind speed. I mean, you did the wind speed measurements of Jupiter and Saturn and the brown dwarf. You didn't show the others though, right?
No, I just showed Jupiter and Saturn.
Do we have them for the other objects?
I think we do. I just think, I mean we didn't really think about, you know, the rocky planets.
What about Uranus and Neptune though? Stacia might be able to comment on the Uranus and Neptune.
Oh, Stacia had to
just
go.
said goodbye. Yeah.
Yeah, and some people are starting to drop off. And so, Johanna, I want to thank you so much for such a great talk.